You can build confidence intervals for other quantities as well, not just for means. I'll show you here how you would build one for a proportion. Let's say you have a random variable x which follows a binomial distribution with parameters n and p. X measures the number of successes in n trials, with p being the probability of a success in one trial, assuming that all of these trials are independent from one another. The point estimator for the proportion is simply the number of successes divided by the number of trials. And that's a mean, if you think about it. Now we know what the expectation and the variance of that random variable are. It would be np and n times p times 1 minus p respectively. Now you can standardize these random variables as well. Like you can look at x minus mu divided by sigma, not the standardization associated with the central limit theorem, but just the actual standardization of a original random variable. You subtract the mean, you divide by the standard deviation. And in the case of x, which measures the number of successes, you can rearrange the terms here and you get that x is equal to n times the estimated proportion. Mu is flat out np, and then the standard deviation would be the square root of the variance. So this quantity here is going to be approximately standard normal. It's not going to be quite standard normal because you're not starting with a normal distribution. If you were starting with a normal distribution, this would be a standard normal, but this would be, roughly speaking, standard normal, especially if n is large and p is a reasonable proportion. It's not a rare event. What that means, if n is large enough, is that the probability that z falls between minus z alpha over 2 and z alpha over 2 is approximately 1 minus alpha. Not quite, because you don't have normality here. This is almost a standard normal. And then you use the same approach as before. And you can build an approximate confidence interval for the proportion 100 times 1 minus alpha confidence interval simply by replacing x bar by p hat. This hasn't changed, and this expression here is the same as this, right? So you build it the same way. Now that's not a super useful expression to have, because in order to be able to compute the term that helps you measure the radius of the confidence interval, you need to know what the true proportion is, and you don't know that. That's what you're trying to estimate. Well, no worries. We're going to replace p by what we think its best estimate is on the left side and the right side of the confidence interval, not inside here. So we replace p by its estimate p hat, the number of successes in your n trials, and then you get a further approximation to the confidence interval. Here's an example that is usually apropos every time election time comes around. Let's see, you have two candidates, A and B. They're both running for office. You conduct a poll of 1,000 voters, which are selected randomly and independently, and you ask them for their preference. 52% of them support candidate A, 48% support their rival, B. At first glance, that looks like candidate A would win, but this is just a sample of 1,000 voters out of the full population. Can you provide a confidence interval for the support of each candidate? So here we'll say a 95% confidence interval. So we use a confidence level of 5%. The point estimate, the number of successes in my 1,000 trials for candidate A, say, would be 52%. That's what we get from the poll. The 95% confidence interval for candidate A would be obtained by just using the formula. It's an approximate confidence interval, and you get the point estimate for the proportion plus or minus the critical value 1.96, because we're at 5% confidence, times, well, the expression here, square root of p hat, 1 minus p hat divided by n. Again, this is meant to be an approximation of sigma divided by square root of n. And if you compute it, you'll get 52% plus or minus 0.031. And you'll get the same radius for the other candidate. It's just that the center of the interval for candidate B is at 0.48. So candidate A here sits at 52, 55.1, 48.9, and candidate B sits instead at 48, 51.1, 44.9. And what we're seeing is that the confidence intervals actually overlap. 51.1 here is actually somewhere here. 48.9 is somewhere here. When the confidence intervals overlap, we say that we can't really differentiate between the two options. You can't conclude that candidate A leads candidate B. The race is actually, statistically speaking, a dead heat. If you had more observations in your sample, if you polled more people, then that would have shrunk the radius of the confidence interval, and you could presumably have come up with confidence intervals that don't overlap, in which case, with probability 95%, you might have been able to say that candidate A leads candidate B, but given the number of observations and given the 4% gap between the preferences in the poll, you do not have enough information to conclude that candidate A leads candidate B. Let's do a quick summary of what we've talked about here. You have a sample of n observations. Your objective is to try to predict the population mean with a given confidence level alpha. If the population is normal and you know the variance, then the exact 100 times 1 minus alpha % confidence interval is the sample mean plus or minus the corresponding critical value of the standard normal distribution, Z alpha divided by 2, times the known standard deviation sigma divided by the square root of n. If the population is not normal, but you do know the variance, and if n is big enough, so if you've taken enough observations in your sample, then the same construction will give you an approximate confidence interval at confidence level alpha. If the population is normal, but you do not know the variance, then you can still build an exact 100% times 1 minus alpha % confidence interval. The difference is you replace the critical value of the standard normal distribution by the critical value of a student t distribution with n minus 1 degrees of freedom, n being the sample size. You multiply by s instead of by sigma, right? So these are the two differences. If the population has unknown variance, you don't know the sigma, and n is big enough, but the population is not normal, or at least you do not know if it's normal or not, then you have an approximate confidence interval, which you can actually build using the critical values of the normal distribution, the standard normal distribution. But n has to be big, and what that means depends on the context. Notice here we're using the actual S instead. And if you do not know the variance of your population, but your sample size is small, you're out of luck. You cannot build confidence intervals that are likely to be very significant, to be useful, to be